Okay, so y'all studied transformations quite extensively in Algebra 2. It was a pandemic, but I think that y'all still, from the little that we've done so far this year, I think y'all have got it. What I want y'all to do, or we'll do this together here, well, just real quickly as a warm up, okay? Take this graph right here, which is obviously a piecewise function graph, and go ahead and tell me, using the three-step definition, whether or not this function is continuous at x equals -1, okay? At x equals -1. If it's not continuous, tell me why. So this is similar to the quiz that we took. Just do number one and we'll do the others together, okay? Get your notation all set up. I'm going to pause the recorder, give you about a minute or so to do that, and we're going to go over. All right, so I'm going to try and catch up with y'all here. At x equals -1, I want you to write out all three pieces, right? So that's going to be the limit as x goes to -1 from the left. And does this function have a name? Jerry? Yeah, I don't see it on the graph anywhere. Typically it's defined. You want to call it J for Jerry or G for Jerry? There's two different Jerrys.
I'm a J for Jerry.
Let's do J for Jerry. Let's call this one J of x, okay? So we got the limit as x goes to -infinity. I'm sorry, the limit as x goes to -1 from the left of J of x. If you call it f of x, that's fine too. And then we got J of -1. And then we got the limit as x goes to -1 from the right of J of x. I'm going to erase this. I kind of beefed up the thickness here. So yeah, beefy. The limit as x goes to -1 from the left. All right, so there's your analysis tools. Now we come in and we evaluate as we approach -1, which is right here from the left-hand side, right? We're coming in. Where are the y values going? Excuse me. They're going down, right? Down to down, down to down, down, down. So -infinity is the better answer. What's another acceptable answer? DNE. Okay, but -infinity is better because it says DNE because decreases without bound. Okay, what about J of -1? Look up, look down, look all around. Your pants are falling down. No, that's a different thing. Look up, look down, right? Y'all remember that? Remember that one? Is there a dot anywhere over here at -1? No. So what would we say about this? DNE, right? And then the limit as x goes to -1 from the right. Okay, save us -1 from the right. We're going where? Up, 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 up to infinity. Okay, so if you looked at the graph before you did the three-step analysis, you would say, obviously, it's not continuous. Okay, obviously. Now, I like this graph because it doesn't have any extra things drawn in there. But based upon our definition of discontinuities, because we got either of those two limits on the roads coming in and the roads going out, what do we know about the graph at x equals -1? What lives there? A vertical asymptote. Yes. Now it's not drawn in there. So when we would do this ourselves, we would draw it in there. And remember, you could do that with your special graphing tool here, right? You could switch. Oh, that's pretty nice. Let's see. I'll make it go a little bit bigger here. So at -1 and it snaps, right? Snap straight. Oh, it didn't snap. Okay. You know what I say when it doesn't snap straight? I go, oh, snap, you know? Oh, there it goes. There it goes. Okay. So we have a vertical asymptote at x equals -1. So it's obviously not continuous, but when we write our response, we don't say that J of x is not continuous at x equals -1 because it's got a vertical asymptote there, right? The vertical asymptote is a consequence of how it's not continuous based on the see, does your snap? Oh, you got yours to snap. All right. So remember, the rule says if any two of them do not equal each other, road, bridge, road, it's not continuous for that reason. Or if any one of them fails to exist, it's not continuous for that reason. Do any of these three exist? No, no. So when we cite that it's not continuous, we can consult any one of these. Which of these three requires the least amount of writing? The DNE one, right? The function value. So that's the one I'm going to use. Okay. So here we're going to say J of x is not continuous We can put the answer first. Where do we just stop there? J of x is not continuous at what? At x equals -1. Yeah, you better say that because it is continuous a lot of other places, comma, because yeah, what y'all said, J of -1, and I'm going to write it out, does not exist or is undefined. Either one. There's no bridge. There's no bridge. Can't cross. Okay. There's also no roads. Okay. So that would be the easiest way to do it. And then again, if you didn't have the graph, but you were given this information, you would look at either the road coming in from the left or the road going out on the right, and you would say, oh, right? You might say, oh, right? J of x has a vertical asymptote at what? At what? At -1? At y equals -1. At what equals -1? X, yeah. Some people are still kind of getting those confused. A vertical line is x equals because the y can vary. You can go up or down as long as the x is right there. And a horizontal line is y equals because the x can vary left and right as long as the y stays at that altitude, okay? So there you go. All right, if we just look at the other two, let's just talk about them instead of writing them down. At x equals 1, just looking at it, is this function continuous at x equals 1? Continuous means connected, right? That's what it means. It's another word for it. Is it connected there? It is. It is continuous. Yeah. The limit from the left is going to be what? What's the limit from the left? 2. What's the function value? 2. What's the limit from the right? 2. Okay. We write all that out. And then we would say in any order, right? J of x is continuous at x equals 1 because what? 2 equals 2 equals 2. We would need all three of them, right? 2 equals 2 equals 2. Very good. Now, when you go on to take calculus, this one is connected in a very dangerous way, isn't it? If this little protective dot were not on there and I were to touch it with my finger, it might prick me, right? Might prick me like, you pricked me. You pricked me, you know? So we would say there that it's continuous, but for later on, store this in your memory, it's not differentiable, okay? All right, and then let's look at x equals 2. Looking at it, obviously, J of x is not continuous there, right? Okay, let's see why based on the 3-step definition. What would be the limit from the left? 3, good. What would the function value be? 3, and what would be the limit from the right? 4. Let's put the reason first this time. Since or because what? 3 doesn't equal 4, comma, J of x is not continuous, right? At x equals whatever we are, 2. And then based upon the evidence that you gathered, the limit from the left is 3, the limit from the right is 4. When your two one-sided limits exist but are different numbers, that's when we have this type of discontinuity, which is known as a what? Jump, right? I used to be able to jump, okay? Now I can barely walk, okay? But I can still skip. I guess that constitutes jumping, right? Technically, you're airborne for a little while. Okay, good, good. One thing I always want to be able to do was slam dunk a basketball, a regulation basketball on a regulation 10-foot rim. And you know what? I never could. I didn't get the jump gene. I could slam dunk a tennis ball, right? But how many times you see people playing with a tennis ball and going, ooh? No, they play with the tennis balls are for tennis, right? Yeah. Now I could slam dunk a basketball over a tennis net. Boom. I never could get the ball sports situation rectified. Never could slam dunk on a 10-foot rim. And now it's a lost cause. My knees are shot. When I have them replaced someday, though, there might be technology that has like grasshopper knees. You know how the grasshoppers, if you ever see their legs, they like, when you open them, have you ever grabbed a grasshopper and say, open your leg? They click. Have you ever heard that? When they extend their legs, they click. They have kind of like some lever in there that boom, that propels them. Maybe I can get some clicky knees, right? That could be like Go, go, gadget, knees, and click, and then boom, take that, LeBron James. A guy can dream. I would settle for getting a suit like this. I'll tell you what, that's drip, right? Yeah, we need some paper towels over here.
He's tripping.
That's right. Okay. Any questions on the warm-up? Any questions on the baby? Yeah. Is that yours that you had when you were growing up? Did you? Yeah. Nice. Is it a boy or a girl?
It's a girl.
Did she have a name?
Brinley.
Brinley.
Yeah.
With an I or an E? Brinley? Brinley?
Why?
Oh, with a Y. Ye Brinley. Okay. Nice. Nice. Okay. Moving on here. Let's talk about the parent functions or the mother functions, right? You can call them mother functions if you want. These are the functions that you are required to know up here in your head without a doubt, indubitably, okay? Because we reference these types of functions throughout the rest of the year to model real life behavior, all right? You already know some of them, right? The linear function is the parent function y equals x, or f of x equals x, right? What do we know about this function? It's a line. What type of line? Straight, right? What type of straight line? Diagonal, tilted, pitched, slanted. Slanted. Why do we make the differentiation between a slanted line and the other type of line that goes like this? Because they're different, right? A horizontal line is of the form y equals a number. We already said that, right? We call that a 0-degree polynomial. But this is a tilted line. The x is there, right? The x is there. All right. This function is a function that has origin symmetry. It's an odd function. Okay, I'm just going to call this an odd function. Does that mean it's a peculiar function? Not necessarily. Okay, the domain is all real numbers. The range is all real numbers. We have a lot of experience with this guy. Okay, number 2, they're not numbered. To the right, to the right, to the right. Okay, x squared. This is probably the most common parent function that you've dealt with, right? We've had a lot of quadratic inequality. The parent function is x squared. What's the domain? What x values work? All real numbers. And you can get that from the graph, or you can look at the equation and say, never dividing by 0, never taking the square root of a negative, right? Now, the range is something that we typically get from the graph, not from the equation. But what is the range of x squared? 0 to infinity, right? Inclusive, right? Okay, good. This function, we say, is an even function. So write that up top there. It's an even function. All right, now look at this guy. The cubic function looks a lot like the x to the first function, but he's the guy that's standing there and his arms get tired and start sagging, right? Ah, my arms are sagging. I called this the disco graph the other day, right? The disco graph, because really it looks like John Travolta, doesn't it? Yeah, in Saturday Night Fever. Yeah, it does. Okay, so what's the domain of this function? All real numbers. What's the range of this function? All real numbers all day long. Yeah. This function is your parent for all cubic functions. Now, cubic functions can actually take on quite a different look than just this right here. They can actually do this. This would also be a cubic function. Why do we call it a cubic function? Because it's x to the third. And we all know that cubes have 3 sides, right? What the? Why do we call something to the third power cubic? (3D). That's exactly right. Say it louder. 3D. I thought it was the baby that talked. Say it louder. But it has a pacifier. It wasn't the baby. It was Maddie. Yeah. 3D. 3 dimensions. Length times width times height. When you have a cube, length times width times height, that's a 3-dimensional quantity. Very good. So we call it a cubic. So they can actually have what we call local max or mins. They don't just have to go horizontal, keep going. This function here is, again, an odd function. Odd function. Yum. All right, so you should know this function. Now look over here. This one is the absolute value function. Absolute value function. And y'all have seen this one before as well, also additionally too, right? This is what I call the V for victory graph. Why? Kinda, right? Yeah, I mean, that's a better reason than my reason. I'm not even gonna tell you what my reason is. It doesn't make any sense to y'all. But yeah, that's a much better reason. This looks like a V, right? It looks like a V. It comes in here with the slope of -1. And then to the right of 0, it looks just like your parent function x, okay? It's actually a transformation, an absolute value transformation on the line y equals x. But it shows up so often in tolerances and distance problems that we include it as its own separate function. So it has a V for victory graph. Is it continuous at 0? It is continuous at 0. It's connected. Now, based upon what I told you, the little preview, it looks like it's a little dangerous to touch there, right? Little dangerous to touch. Based upon what I said earlier in calculus, would you say that this function is or is not differentiable there? What happened on the last time there was a point? I didn't want to touch it. It wasn't differentiable. This one we would say is also not differentiable. You don't need to know that in this class, but hey, moving forward, right? That's where we're all heading. We want to focus on the future, right? Because that's where we're going to spend most of the rest of our lives. Okay. This function is an even function. Even function. Yum. Yes, waitress, can you bring us some more even function over here to the table? Thank you. Yum. All right, let's go to this. Oh, we know this guy, right? The reciprocal function. Oh, by the way, what's the domain of this function? Absolute value domain. All real numbers. And the range? 0 to infinity. Everything greater than or equal to 0. Good. All right. We met this guy the other day, or we reintroduced yourself to this guy the other day. 1 over x is called the reciprocal function because all it does is it takes your input and flips it, right? Flips it. Now, there are a couple of features on here that are very, very important, aside from the graph that you see here. What are they? What forces the graph at 0 to go straight up and straight down? A what? Vertical asymptote. Yeah, so let's see if we can draw that here. Whoa, look at that dude. Okay, and the reason this came up the other day when we were talking about end behavior is what happens to your y values as you head out to the right or left. They get smaller and smaller and smaller, approaching what? 0. So it has a what also? Horizontal asymptote at y equals 0. Okay, so aside from the way the graph looks, you need to remember that this graph has both a vertical and a horizontal asymptote, essentially on the x and y axis. Okay. Now, this function is also an odd function. Odd function. Delicious. Okay. Yum. Yeah, it's better. Good thing I'm not a jingle writer, right? I'd be hungry all the time because I wouldn't make any money selling jingles about food. Oh man, the irony. Let's see. What's the domain of 1 over x? The domain. What's the domain of the reciprocal function? What values of x does it take on? Well, look at the equation. What value can we not use in the denominator? 0. X can't be 0. You know why? Because there's a what there? Vertical VA, right? VA. What's the range of this function? Everything except 0 again. Okay. Y cannot equal 0. That's the range. Again, we get the range typically from the graph. It's a lot harder to get the range from the equation because it's the dependent variable. We have to kind of think of what the outputs look like. All right. And now we're going to introduce you to our next course of study. Is going to be exponential functions followed by logarithmic functions. You said logarithmic functions or log functions for short. That's how we're going to end this first semester, studying exponential and logs. And we study one of them right after the other one for a very good reason. This is an exponential function because it has a variable in the exponent. We looked at 2 to the x the other day, right? 2 to the x. It doubles like mitosis, right? Cell division times 2 times 2 times 2. Your parent function is going to be e to the x, okay? Now, some of y'all have experience with e. E is called Eulers, named after Leonard Euler, the most prolific mathematician of all time when you include individual work, okay? Euler's constant, Euler's number, same thing. It's the second most famous irrational number in all of mathematics behind pi. We call it a transcendental irrational number. Do y'all know what it is approximately? 2.718 ... So it's between 2 and 3, right? It's closer to 3, 2.7. All right, now sometimes this is called the banker's number because of compound interest. This would be the rate at which money grows when it's compounded continuously. Populations grow according to this number. So it's called the natural base as well. Euler's constant or the natural base. It shows up in nature, okay, quite a bit. There's a lot of different algebraic ways to write E, but Euler discovered it kind of as doing accelerated compound interest. In fact, this is what it's equal to, if you want to know. It's also equal to this. It's equal to the limit as n goes to infinity of 1 plus 1 over n to the nth power. Okay, y'all recognize the limit there? Yeah, and then the formula that you have behind it is the formula for compound interest, okay, of money. So that's why E is sometimes called the banker's number as well. But it's a very important number. To us, we're going to prefer E over pi, unless we're eating, right? And then we prefer like chimichangas over pie, right? The pie is still good. I don't know. That just came out of nowhere. I guess I'm hungry. All right. You never had a chimichanga? It's like a fried burrito. Yeah. You take all the good stuff in a burrito and then deep fry it. Yeah. Yeah. Oh, yeah. Yeah. My brain goes all over the place. I should have said cake, right? Instead of chimichanga. But they both start with C. Okay. So this is going to be the parent function for all exponential. Guess what it has on the x-axis? A horizontal asymptote, right? We talked about exponential functions. Oh, that didn't show up very well. We talked about exponential functions having a horizontal asymptote, but only affecting the graph on one end. Same thing here. This parent function has one horizontal asymptote. It's on the x-axis, but for growth functions, it only affects the graph on the left, okay? Things go to infinity very rapidly for positive values of x, and things go to 0 very rapidly for negative values of x, okay? In the long run, exponential functions will end up growing faster than like any polynomial function, okay? Now, the log function was designed to slow down exponential growth, okay? In fact, the log function ends up being the way to undo exponentiation, right? Like if you multiply by 5 and you want the 5 back, or you want the number, you divide by 5, right? Multiplication and division are inverses. If you add something and you want it back, you just subtract, right? Addition and subtraction are inverses. If you exponentiate something and you want it back, guess what you do? You log it, okay? Logs and exponentials are inverses of each other. And that's why we study them on the heels of each other. So get this, because the exponential function e to the x has a horizontal asymptote on the x-axis, its inverse, which we call the natural log of x, I'll talk about that a little bit more here in a second, it has a vertical asymptote on the y-axis, okay? And watch this, because e to the x has a y-intercept at 0, 1, the natural log function has an x-intercept at 1, 0. See that? So we'll study inverses again later. Does anyone remember from algebra 2 how you can get the graph of an inverse from a function? It's a reflection. Do you remember? Maybe your teacher didn't tell you because they're like, oh, pandemic, we're not going to give you too much information. A negative out front would flip it across the x-axis.
Like from an explosion.
Well, yeah, basically there's a line that you could take to flip this across that line, like a mirror image, to get from this graph to that graph. It's not the y-axis, right? If you flip this across the y-axis, you just get exponential decay. If you flip this across the x-axis, it kind of looks the same, but now it's pointing in the wrong direction. Yeah, so let's talk about that. You know how to find an inverse algebraically. You take out f of x and you replace it with y. And then the money step is you interchange x and y. You interchange them, and then you resolve for y. Okay, when you interchange them, that's like having a 0, 1 becoming a 1, 0. All the points get changed. So when you then interchange and resolve for y, you're undoing all the steps and you're getting the inverse. But graphically, and I'll show this again later, but graphically, all you have to do is reflect it across the line. Here, let me see if I can do this better. I actually have a grid here. There you go. If you reflect it across the line y equals x, you'll get the graph of an inverse, okay? So I always thought this would make a good yearbook photo. Look at the exponential graph e to the x and turn your head at a 45-degree angle. And yeah, there you go. Yeah, don't hurt yourself. And then imagine flipping that thing across that line y equals x. Guess what graph you're going to get? You're going to get log, yeah, okay? So you reflect it across the line y equals x. Now, why the line y equals x? Because y equals x is its own inverse, and it's also the identity graph. It's your parent function, y equals x. He's pretty important, okay? Now, let's talk about natural log of x. That's how we read that. The natural logarithm, okay? You've seen logs in a different way before. This is actually the same as log base e of x. That's how we're going to read it. So it has the natural base. That's why we call it the natural log. But we write it ln, logarithmic naturalis. That sounds pretty Latin-y, isn't it? That's where it comes from. Natural log. It looks like it should be NL instead of LN, right? But apparently in that language, they flip it around. Logarithmic naturalis. It's log base E, right? Now in your science class, you've seen this, right? You've seen a log that doesn't have a subscript or a base written, right? When you're studying like pH levels of acids and bases, this shows up quite a bit. If you're studying earthquakes, anyone ever study earthquakes? Yeah, maybe, or sound and decibels. A lot of things deal with this log. This is the common base. If you don't see a base, but you see log, guess what the base is? Anyone remember? 10. Good. There's an implied 10 there. So those are the only two logs that you can write without a shown base, okay? Log base 10 can be log of x, and then ln of x is log base e. Everything else, because they're logs of other bases, just like there's exponential for other bases, they all require a visual subscript. So anyway, guess what the domain of e to the x is? All real numbers. Guess what the range of the natural log is? All real numbers. Whoa, hey. Guess what the range of e to the x is? 0 to infinity, inclusive 0 or non-inclusive? Non-inclusive. Guess what the domain is for the natural log? 0 to infinity, non-inclusive. See, that's what happens when you interchange x and y. All the x information for one becomes the y information for the other, and vice versa, okay? In fact, the x and y axis themselves interchange. If you take a vertical line or a horizontal line and reflect it across the line y equals x, it becomes vertical, okay? So those are inverses of each other. Right now, I just want you to know what the shape looks like, okay? Because that's going to comprise the rest of this 9 weeks, pretty much, studying those two functions and their application. Sound good? And then we'll finish off with this little fellow that we met. This is the square root function, okay? It starts at the origin, and it comes out vertically and goes to the right. What's the domain? 0 to infinity, inclusive or non-inclusive? Inclusive. And what's the range? 0 to infinity, inclusive. Yeah. Now, this one looks like a parabola, half of a parabola that's literally fallen over, but that's not how we get it. We get it by taking this. If you come up here to x squared and you draw that line y equals x, oops, I have it in the wrong place. There you go. If you take that graph and reflect it across the line y equals x, the piece that's intersecting the line right now becomes that piece over there. Okay. And we don't look at the negative piece because, hey, there's my friend. Because then it wouldn't be a function. So when you take the square root of a number, you're going to get the indicated positive root. But it's not a parabola that's fallen over. It's this branch of the parabola, not the one on the other side, that gives us that. Okay. You can actually demonstrate that with a sheet of paper. If you just take a piece of paper, do a parabola, draw a 45-degree line, hold it in the top corners, like y equals x corners, and just turn your wrists. Okay. And you can do that when you get home, like impress your friends and family. We'll do that little activity later in the year when we talk about sine and inverse sine. But anyway, inverse is pretty cool. You ever wish you could take something back? No? Oh man. Fist bump, man. That's awesome. Yeah, I sure do. Well, in life you can't, right? In life you can't take something back. But in math you can. If there's an inverse, you can undo what you did. Okay. All right. Now let's look at all the ones that I called even and odd functions. Those last three, they're neither even nor odd. What I want you to do is either remember, or based upon the shared characteristics of the one we called even and odd, what does it mean to be an even function? What does it mean to be an odd function? This is where normally people do like a think, pair, share, right? Get with your buddy, yeah, talk about what you had for lunch, and then hope the teacher doesn't call in, right? Okay, yes, what? Okay, yes. It has something to do with the degree. Yeah, very good. Because if you notice on the odd function, what's the exponent on the x? 1, which is an odd number. Look at x squared. 2 is an even number. Look at x cubed. 3 is an odd number. Look at the exponent on the x and the absolute values. It's a 1. 1 is an, oh crap. It breaks down. But over here, it's x to the first and it's odd. Okay, it breaks down. Okay, but that has something to do with it. Believe it or not, it does have something to do with it. What else do they have in common graphically? What's that? The vertex? Oh, they all of these up here pass through the point 0, 0, right? Vertex 0, 0, 0, 0. This one does not pass through 0, 0. So that's a good characteristic to recognize. How about, what, go ahead. Oh, that has something to do with it also. Yeah, yeah. If you notice the ones that are odd, they do this, as you were saying. They have opposite, what do we call that? The way it goes out and comes in. End behaviors. Yeah. They have opposite end behaviors, right? Bottom in, top out. Bottom in, top out. Kind of bottom in, top out, right? Yeah. And then the ones that are even, top in, top out, top in, top out. Same way, right? That does have something to do with it. Let's go back to this one here, where I said you could get the graph of the natural log of x by reflecting it across the line y equals x. What do you notice about the even functions? I kind of blurted it out earlier, but I was hoping no one was paying attention. What do you notice about the two even functions, x squared and the absolute value of x? Is there a line of symmetry anywhere across which you could fold the graph and have it coincide with itself? Yeah, what is that folding line? X equals 0. Good. You didn't even say the y-axis. Good. These have y-axis symmetry. Okay. An even function has y-axis symmetry. Y-axis symmetry. All right. So then that takes us to the odd functions. Now that we're thinking about some type of symmetry, if the even functions have y-axis symmetry, then the odd functions must have X-axis symmetry. Oh my gosh. If a function had x-axis symmetry, let's see. Yeah, here's quadrant 1 reflected. Uh-oh, fails the vertical line test. Okay, a function can't have x-axis symmetry unless you're one guy. There's one function and only one function whose family members also apply, but there's one patriarch, one function that does have x-axis symmetry that is a function. Okay, I'll let you think about that. Okay, so they don't have x-axis symmetry, but they do have another symmetry, right? Watch this. Take your iPads, hold it up in front of you, and look at the graph of y equals x, all right? Now, with your right hand, take the wheel at 11 o'clock and make a hard right turn. Hopefully your screen lock's on. It's not? Oh, now look at your graph again. If your screen lock's on, it looks what? Same, right? Yeah, yeah. Now, come over here to x cubed. Put it back in its normal position. Reach up there at 11 o'clock, make a hard, no, let's do it the other hand. Grab with your left hand in the top right corner, and now make a hard left. What do you notice about that graph? Same, okay? So those have, and oh, we don't want to leave this guy out. What about me, right? Turn it upside down, it's the same. Yeah, there you go. There. So the odd functions, they have a rotational symmetry, okay? Odd function has rotational symmetry. And how many degrees did we rotate it? 180 degrees. 180 degrees. I remember when Jason Kidd, he was first drafted by the Dallas Mavericks. And Dallas Mavericks, they didn't have Luka Doncic, they didn't have Dirk Nowitzki back then. They were pretty bad. But Jason Kidd was going to be the savior. And they asked Jason Kidd, you know, what his plans for the team were. Now that he's on him, he says, you know what? I'm going to turn this team around 360 degrees. And we're like, oh man, oof. I hope you do better than that, right? So it pays to know what 180 degrees is, right? A direct about face. So those are the two symmetries. Now, why is symmetry important? Can anyone guess? Is it important, or is it just a characteristic that's a curiosity? That too, right? Mathematicians love looking for patterns. Why are patterns important? So we can put them on our clothes and look stylish, right? Yeah, that's a fabulous sequence pattern. If we can recognize patterns, we can replicate. Yeah, we could duplicate, replicate. We can predict. We can anticipate. Yes, yes. We can plan ahead. Yeah. So symmetry is just a characteristic that helps us do that, right? If you know a function is an even function and that it has y-axis symmetry, if you know what the graph looks like in quadrant 1, you know what the graph looks like in quadrant 2. You wouldn't have to go there to get values. You could just use the ones in quadrant 1. In real life, it might be difficult to get values from a certain, scenario, but by using symmetry, we can actually get those values without going there. So it's an aid to sketching, right? If you were sketching a graph and you only had information, let's say in quadrants, 1 and 4, but you knew it had rotational symmetry, you would know what the graph looks like then in quadrants 2 and 3. Okay. All right, how are we doing on time? What time do we get out of here? 5 minutes. Wow, time flies when you're doing math, don't it? Yeah. What's the difference between doing math and having fun? There is none, right? It's just the same, right? Okay. Now, once we have these parent functions, what can we do with them? We have them memorized, yes? We can start graphing things, okay? Let's look at this last one here, and this will be the last one we do for the day. This is a piecewise function, right? And it's not a single-headed baby, remember? It's a triple-headed baby. Triple-headed baby. Not as cute as that one there, in all fairness, Miriam. It's part x cubed, part x squared. This one actually changes at what two values? 1 and -1. Yeah, this should be a negative up here. This should be a negative right there. Add that little negative. Oopsie. Okay, So good. It's changing at -1 and +1. Here's how we sketch the piecewise function. Give yourself an X and Y axis, and then go to the values of X where you would buy a ticket to see this baton exchange, right? Here's -1, here's +1. Give yourself some room as well, like stretch it out. Don't draw the 1 and -1 too close to the X axis. Okay, now to the left of -1, do we know what the limit is as X goes to -1 from the left? Yeah, left than is left of is less than. Plug in a -1, what do you get? You get -1, -1. So at the point -1, -1, do I put a solid dot or an open circle? Open, because it's strictly less than, right? So I'll put an open circle right here. And now I know that to the left of that point, it looks just like our old friend, senior line. So you could just draw a line coming in with the slope of 45 degrees or 1. Okay. All right, now let's look at the next piece. Between -1 and 1, it's X cubed. Let's see if we can figure out the right-sided limit from -1. You can read this from the inside out, yes? It's the better way. X is greater than or equal to -1. So what's the limit from the right of -1? It's -1 cubed, which is what? -1. So I can plug the hole. And then let's do the other limit. It's also equal to. So what's the limit from the left of 1? Plug it in, you get 1 cubed, which is 1. And because it's less than or equal to, we put another solid dot. All right, now that we have those two solid dots, we know it looks like X cubed in between there. So do y'all remember what X cubed looked like? That was the wiggle guy, right? John Travolta. See that? So it's going to look like this. It comes in like this, goes horizontal, and then symmetrically comes up like that. All right, and then finally, to the right of 1, it's X squared. Well, let's figure out where it picks up, okay? What would be the limit from the right of 1? Right of is greater than. Plug in a 1 and you get 1 squared is 1. Now, based upon the definition, do I put a solid dot or an open circle there? It's strictly greater than. So I put in open circle. Oh, but there's already a dot there. So guess what? They're going to share it. Only one can claim it, but they get to share that point. Sharing is caring, isn't it? And now I know what X squared looks like. It would kind of come up like this. You know, you can imagine like drawing it going through the origin, but you don't want to draw it over there. So there's what the graph looks like. Yeah, it is cute, right? It's super cute. It's like Brittany cute. Brittany. Brenly cute. Okay. Brenly cute. What's the domain of this function? All real numbers. And what's the range of this function? All real numbers. Okay. We didn't get to transformations, but you know what? We'll get to that some other time. You know your parent functions. If you don't know them, memorize them, memorize them, memorize them. Because once you have these memorized, you're going to be able to lightning quick sketch graphs of transformations. All right. Thank you all for y'all's captivity today. I appreciate it. And yeah, y'all can go. Bye-bye.